Hello, and welcome to another openFrameworks audio programming tutorial. Today, we will be discussing interpolation. Interpolation has many applications in audio and video programming. It is the act of observing data at a given number of points and suggesting values for positions between these points. So for an example, we have 9 randomly generated samples, audio samples. All right, so there's randomly generated. So there we go. In the worst case scenario, which is what we have done, or what we did in the previous tutorial, we truncate the result. So you can see read point 0.86, we are chopping off everything after the decimal. So we're getting the height at point 0. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 to 8, 9 points. So when we truncate this, we're getting this height value. So when we get to above 1, everything's truncated. So from here to here, we are getting this value, even though we're closer to this. Which brings us to the next best option. Instead of truncating or chopping off everything after the decimal, we could round. Alright, so now it's above 1.5, so it'll go with the nearest sample. And let's show a drawing of that. So this is a little bit better at almost no additional cost for the CPU, as we'll show later. That's still not good. We are still getting a high frequency jump here, this will provide high frequency content that is not necessarily present in the audio. So the next best solution would be to interpolate linearly. So if we have a point here and a point here, we can just draw a straight line, and that will be the point. So if our x is here, we reach that point in the line, and that will be our y value. So here we go. And then when we go from point 0 to point 1, we're on this line. So this is already significantly better, and this actually doesn't cost too much for the CPU either. Just I think 2 multiplications, an addition, and a subtraction. So that's not bad. Let's show the line there. Generate random samples. Alright, so there's still a bit of a problem. We do have a high frequency jump from here to here, and that might not be what is the best way to represent the audio. However, this is usually sufficient enough that any noise generated from this method will be inaudible, and it's very CPU efficient. So most of the time, this is the interpolation method used. And there's one that is typically used that is slightly better, not slightly better, a lot better than this. This is called cubic interpolation. So instead of drawing a straight line between these points, if you can kind of imagine freehand drawing the smoothest curve you can through these points. Free mousing in this case. And it's easy to freehand draw or to imagine these curved lines. It's a little more difficult to calculate them. And in fact, it's very expensive on the to ask the CPU to do this every sample. Whatever we ask the CPU to do, it has to do that 48,000 times in 1 second at the sample rate I usually run, 48K. So let's go ahead and draw the curved line. And we can see this is very smooth. So it's eliminated that high jump problem when we transition from this segment to this segment. Alright, so observe a couple different plots. So this is a pretty good method. And there is not going to be a perfect method. We have only stored audio samples at these locations. So there's no actual way of being 100% certain on what this point should and definitely be. We are interpolating, so it's kind of like upscaling. So if you imagine an image, a 400 by 400 pixel image, and trying to scale that to a 800 by 800, we can make an educated guess on what those missing samples will be, but there is no way of actually knowing what they will be. Same way with audio, when we're upscaling here, there's no way to be certain. But this is the best method to approximate with the lowest noise content. Okay. So a couple of concerns let's go back to linear for a moment. When we're doing linear, we only need to know the value of the surrounding sample. So we need to know the y value of the sample and the y value of this sample. And we know that the x values are 1 away, since these are stored in integer indices. So it doesn't take much information. However, for cubic, we not only need to know the next sample and the previous sample, we also need to know 2 samples forward and 2 samples back to generate this curve. So that's not a huge problem, we just get the samples, but you run into a couple of issues. What if I want the point I'm on right here? We can get the 2 samples forward, but there aren't 2 samples back. And the same thing on the other end. We can get 2 samples back, but we can't get 2 samples forward. So that's a problem that has to be dealt with. My solution in this example is to, if this sample, this imaginary sample, is not available, just copy this sample and use it twice. And the same thing on the other end. If 2 samples ahead's not available, just copy this one and use it twice. And that's sufficient. It's not the best method for a wavetable oscillator, but we'll get to that in another tutorial. Okay, so this should be posted in the description eventually. It won't be when I first post the video, but I'll eventually get it on there. Right now the code's not too friendly because I had to do it fairly quickly. But let's open where we left off on the last tutorial, our sound file player. Everything should still be playing. And let's go ahead and make sure that's true. I will use a short sound file this time. Great. And let's go ahead and listen to what the problem was. That's fine. I wish I would have paid attention to which sound I had just opened. But let's use string flick, sounds promising. Alright, so the high frequency content there. You can definitely hear some truncation errors. The high frequency content there is generated by those quick and sudden jumps of a truncation interpolation. So we'll need a couple tools. So let's go ahead, we don't have this in our document yet, but let's add our audio tools document. So if you're following along, just grab that from another document. If you're not, you can grab the starter file from the description. So that was in the additive synth file. The current file we're working on is sound file player, and mine at least. You may have called it something else. So go to the source folder of the current project and copy in our audio tools. Once those are copied in your source folder, make sure your project knows where to look for them. Great. And to use these extra documents we just added, we need to add something in our header. Okay, and let's go ahead and make sure it runs, just to make sure that's linked properly. No complaints. Okay, so let's add our linear interpolation function. I haven't deleted them. Spoilers. Alright. So, we want to take in 2 x values. Well, first we'll start with linear interpolation. We need the sample before and the sample after what we're trying to access. And we want to return the interpolated sample. So we'll return a float. We'll call this linear interp float x0 float, oh not x, sorry, float y0 float y1, and then we need a float current x. And then we'll do this function. Alright, everything looks happy. This will not be part of a class. We don't need to store any values in this, so we don't need to use this as a class. Okay, so we just have our function here. And we need to, for linear interpolation, well, we already know we need to return, let's call it result. Let's say interpolated value. No harm in using a lot of words. Float interpolated value. Actually, it's a good time to mention that since I brought it up. There used to be harm in using a lot of words, and that IDEs didn't fact check you like they do now. However, I don't usually even have to type. If I want to use that word again, interpolated values, I only have to type the first 4 letters and it suggests it for me. And if I misspell it, it's going to show me that it's misspelled. So now the IDEs can do that for us. I like to use big, long words. If you look at a lot of C tutorials, it's pretty common to call something A, B, and Z, or something like that. And just because you can't misspell A as easily as you can misspell interpolated value. Alright, so that's just my personal preference. I am pretty alone in that, but I will stand by it. Alright, so we need another value. We'll call this scale value. Okay, so this value will be the proportion we are from the first sample and the next sample. Here I have a shortcut. Since we know that this will be integer values and there will be integers in a row, we can use this trick I made. I'm sure someone else has come to the same conclusion. Current x minus a truncated version of current x. Alright, so what this means, if our x is, say, 50.6, this will be 50.6 minus 50. It chops off the 6. So that lets us know we're 0.6 in between the previous sample and the next sample. So that's a pretty handy trick. Alright, so we have our interpolated value. Let's make interpolated value equal to, we have to make a proportion of the y value at the previous x and the y value at the next x. So put these in parentheses just to make it clear. Y0 times 1 minus scale value plus y1 times scale value. Alright, so if you look up linear interpolation on a web page, it will not be, there will be a lot more steps than this. I'm able to take shortcuts because I know we're using integer values for x, and that's actually basically it. So, but I've narrowed down the process to just 2 multiplications, 2 subtractions, and an addition. So pretty efficient. And since we have to call this function so often, and it's not a large function, let's make it inline. Great. Alright, so keep my document a little tidier. Alright, so we have our function, linear, and linear interp is what I said, not what I typed. Alright, so let's use that function. Okay, so here we have our current sample. This is what we were doing before. We were just truncating our reader position and chopping off everything after the decimal. That's not what we want to do anymore. So let's make floats y0 and y1. If you want to make them in a list and not assign them yet, you can just put a comma. You can write as many as you want here. So that's the same thing as saying it's just a little bit quicker and it takes less space. Alright, so y0 equals, we're going to get the y at the previous x position. So go to our mono file, mono audio file, previous, so let's truncate like we were. Alright, so if we're at sample, let's do 50.6 again. this will get the sample at integer location 50. Now we need to get the sample at integer location 51, knowing that. So y1 equals mono sum at int read point plus 1. Alright, so we have our previous y value and our next y value. Okay, and we need to assign our current sample to a linear interpolation of these two values. Linear interp y0, y1, and read point. Alright, and that should do it. Alright, there will be one problem. Let's go ahead and try it first. Right. So we are accessing read point plus 1, but this array may not have that sample, and that's what you just saw. So we need to make sure we're only trying to get the read point integer truncation of the read point plus 1 if it's there. So if read point is less than mono sum files dot size minus 2, so now we're only going to grab that if it's there. However, if that's true, do this. Else, if that's not true, not plus 1. And we know this will always work because we did some checking here. There we go. Okay, so we made a little safety there. Our code's getting a little ugly, but that's fine. So we're not getting that high-pitched frequency content anymore when we're going very slowly. So I have the speed printing to the console here. It's pretty acceptable. Okay, so we've successfully made a linear interpolation function. So the next step will be to add our cubic interpolation function, and it's a little scary. Math-wise at least, but let's go ahead and do it. This is one of those situations where you don't have to understand the math to use the math. Alright, so we're going to want another return our interpolated float. We'll call this function cubic interp. And we're going to need a few more values. Like I said in the demonstration, to do cubic interpolation, we need to know the previous two and the next two samples. So we'll call those float y0, float y1, float y2, float y3. So 4 samples we'll need to do this. And we'll also need, again, our current position, current x. And this will happen all the time, 48,000 times a second in this example. So let's go ahead and try to do an inline. Whether or not it will actually do this when it compiles, it depends on the compiler. Compilers don't like to inline really large functions, but if it doesn't want to, it just won't. So I don't think this will hurt us, unless the compiler is very bad, which I don't think this is. But we'll try anyway. This might be in a category of too big to be inlined. All right, so I'm going to copy and paste the code here because I am not that brave. I got the wrong code. Okay, just like that. All right, get rid of this, and let's name these the same. Float interpolated value, and that's what we'll return, our interpolated value. All right, and I use current x instead of x. All right, so here it is. We have our 4 coefficients. And if you're really into calculus, you can check out the math on this. I don't happen to be unless I need to be. But I will go ahead and make this pretty big. All right, well, never mind. I guess I can't do that. Where is there a zoom function? There we go. Let's do 200% zoom. And that way you can pause and add this to your code. Okay. Make sure everything's okay here. Right, so what we'll need to provide is the sample before, 2 samples before, the sample after, and this is the y value, and then the sample after that, and our current reading position, and it will return our cubically interpolated sample. So go ahead and comment out what we had before. All right, so we need y0, and that'll be 2 samples behind. So mono summed at truncate read point. So that's 1 sample behind since we truncated. Minus 1 is 2 samples behind. Y1 and finally we'll need 2 samples ahead. All right, and we commented out our y values here, so let's go ahead and make those. All right, looks happy. So as we had a problem here, we will also have a problem here. We could be trying to access, and in fact we will be at some point, samples that are not available to us or that don't exist in this array. So we need to protect against that once again. So how do we protect against accessing 1 behind or 2 behind our current sample? If read point is greater than 1. All right, so this will guarantee that this will not access a point that's not there. And otherwise, if it is less than 1, don't know what that was. All right, y0, actually it's copy and paste. All right. This should be safe. The truncated read point should be protected by this check down here, so we don't need to add anything there. But as we discovered here, we do need to protect against this. So I'm going to copy that. And this is y2. Alright, so this is 1 sample ahead of the current position, and y3 is 2 samples ahead of the current position. but we do need to finish this. I should have copied it, but I like to put else on the same line. I don't know why it automatically does that. All right, so quicker just to copy and paste this. So we're going 2 ahead, so we need to do -3, 2. All right, and this would be fine, but we can do some additional checks to grab the nearest sample. So else if read point less than monosum dot size -2. Instead of going 2 ahead, we'll be fine with 1 ahead. And if that doesn't work either, we'll just put our tail between our legs and take this. All right, so that's a lot of work. You can see the first 4 lines we wrote weren't so bad, but we need to perform some safety checks to make sure we're not accessing a point in the array that's not there. All right, and now we got to finally use our cubic interpolation. So our current sample equals cubic interp, and that takes a few arguments: y0, y1, y2, and y3, and finally our current position. Looks happy. All right, let's take a listen. Likely we will barely be able to notice a difference if we can at all. Huh. The variable y3 is being used without being initialized. Ah, indeed it is. All right, so I did copy and paste without being responsible and changing what I needed to change. All right, and then let's make some comments. Y3 safety check. Y2 safety check. Okay, now it should be good. Great. So now we've implemented both linear and cubic interpolation. It would be a good idea to test this and see which one is appropriate, which one we like better, and compare. We've only done 3. We never did the rounding, but it won't be necessary. So let's make some kind of solution to switch between the interpolation modes. All right. So I'm going to introduce a new term called enum, short for enumerator, and then we can list our types here. So let's call it truncate, linear, and cubic. All right, so the enumerator is like the U menu in Max. If I click on, or not click on, but if I select this, this is assigned 0, this is assigned 1, and this is assigned 3. And a lot of the times I'll fix this. You see these capitalized. It doesn't have to be, but stick with convention. So when people see that, they know it's part of an enumerator. All right. So whenever I use the word cubic, it's going to replace that word with 3, or 2, sorry. So that's good to know. What else do we need? We need a way to switch these. So do we still have our key pressed? Yes, we do. So go to your key press function. Where is that? Here it is. Oh, okay, so we're already using spacebar. All right. One last thing, sorry. We'll have to store our current mode in an integer. So int current interp mode. All right, so we'll introduce yet another element of C++ programming, and this is also available in C. So is the numerator, by the way. This is called switch. We're going to switch between our current no, we won't. We'll switch between the current keyboard input. All right, so the switch is kind of cool. It does what you'd expect. So we're getting our key from this function. So whenever you press a key, that key is stored in the word key as an integer. All right, so we're going to switch key. And the way the switch works, we have a case, and this is asking what key is pressed. And if the key was pressed, let's do 1, full colon, do what we want to do. So we need our current interpolation mode equal to truncate. We could write 0, but this way is a little more easy to read, easy to see what's going on. And then after your case, you break. All right, so if the key pressed is key 2, and key 2 is just the number 2 on your keyboard, since I put that in single quotes, the current interpolation mode will equal linear. And you see, since we made the enumerator, that it automatically knows what these are. And then break. And finally, case 3, cubic. And again, we'll break. Okay, and when you use a switch, there is another element called default. And default is called if a key is pressed, but it's not one of these 3. And we use an if statement for the spacebar already, but we could have added that to this, but we won't change that now. But default is called if a key is pressed and it's not a member of any of the things we've added. So if we'll go ahead and protect against the spacebar, it won't matter. But if key is not equal to spacebar, well, and then we'll give a warning. Key input not supported. All right. So, and we'll also break. We don't really have to, but it's good manners. All right, so we didn't have to add this to our switch statement. It's just good to have a default. Okay, so we could have used an if statement for this, but there's a couple of advantages. If we're using if statements, it will have to check every single condition. Since we're doing it as a switch statement, it's going to find what's true, and if it finds what was true, it's going to break out of the switch and not keep going. So it's slightly more efficient, and it's a little more clear, I think, as well. And we'll be using another switch statement in our audio loop. So go up to your audio loop, and we'll need to add a switch statement. So that's interesting. I'll add it here. Switch interpolation mode. Oh, whoops. Not what we wanted. What did I call that? Current interp mode. So in our audio loop, it'll find the current interpolation mode. We'll put those all here. So case see if it's truncated. And then we'll want one for linear. And we'll want one for cubic as well. All right, so if it's truncated, we'll do what we had at the very beginning, which will be current sample equals mono summed sound file at location read point, and this is truncated to an integer. All right, so very simple, but not very good sounding. All right, so if it's linear, we want to do this. All right, so let's go ahead and make our y values above all of this. Okay. And then we want to set our current sample equal to a mono summed. Sorry, that's not true. Linear interpolated value, linear interp, and we'll give it y0, y1, read point. All right, and we don't need this anymore. Cubic interpolation. All right, so there's a lot going on here, but it's pretty clearly labeled. All right, so for truncating, we're going to do this. If we're linear, we're going to do this. If we're on cubic interpolation, we'll do all of this. All right, let's add a default case. So if something does go wrong, we'll know, and this should never happen. But we'll set current sample equal to 0 in a default case, and we won't see out anything because this will be, if that does for some reason happen, it'll try to print to the console 48,000 times a second, which is hazardous. It actually will make an attempt on Windows. When I tried that on Mac, it crashed pretty hard. So just don't do it. Yeah, that's a good lesson. Don't see out in your audio loop, especially at the audio rate. All right, so this is my first time trying this, so this will be interesting. So if we press 1, we get truncated. If we press 2, we get linear. If we press 3, we get cubic. So this is our truncated. Here's linear. And here's cubic. Linear is actually sounding the best right now, which is a little surprising to me. All right, let's double check. Maybe I've done something wrong. And then if not, then we can try to make a case for that. It's interesting. So it could be just the fact that we are interpolating noise. But I don't have an answer for that. That's interesting for sure. Let's do one last thing. Just to verify. Alright, and then I'll stop printing the mouse value so it won't get confusing. Let's do string flick lower. That sounds promising. So this is truncated. Definitely bad. There's linear. Yeah, it's really interesting. So linear is working best. And I'm actually not hearing any difference between cubic and truncating, so I would assume something's wrong. But that'll wrap it up. If I find out what was wrong, I will append it to this video. Next time we'll be adding biquad filters to our audio toolkit. See you then. Okay, found it. So the problem is we were not using our read position, we were using read speed, which would give it the same x position between x1 and x2 every time, because we weren't changing the read speed per sample. And the x position should change. So let's change that to read point, and we should have more success. All right. So here's truncating. Here's linear. And here is cubic. Linear. Cubic. Cubic. Linear. So I'm not sure how the audio will turn out because it has to go through two different compressions, one to do the screen capture and one to do YouTube. But on your own system, you should hear a distinct difference between linear and cubic. However, you'll have to determine, based on the situation, if it's worth the extra processing to use cubic. All right, so if we compare the two, we can see we can actually get rid of a couple things here. You can see how simple our oh, whoa. Okay, how simple the linear interpolation is compared to our cubic interpolation. Note that we have to use exponents twice in this equation, so that's very expensive. And we're also doing significantly more multiplications, additions, and subtractions. I haven't gone to any significant amount of work to make this more efficient yet. However, there's the bottom line that we'll not get this much more efficient no matter what we do. So this is significantly more cumbersome. And there are other methods to try out. One being cosine interpolation, which I'll not include. But these are two very popular interpolation methods. We are getting better results, in my opinion, from this, but perhaps not enough better to warrant the extra CPU usage. So if you're doing something in real time, you're going to want to preserve CPU where you can, and this will definitely be your option. If you're writing an algorithm to do something, or you just don't have much going on in the first place, by all means use cubic. Alright, so there it is. Finally, it took me a while to find that. But next time, we'll be doing biquad filter. Thank you.